Good afternoon, everyone. So my name is Siva Poornan. I am a doctoral student at the Civil Engineering Department of IIT Madras. So I welcome you for the third week interactive session on for the course of Matrix Method of Structure Analysis. So here we are back here after 2 weeks of interactive session. So we were discussing on basics of structure analysis in both the weeks, and yeah, so basically we were revising what we had seen earlier course, how to analyze a statically determinate structure, stability, static determinacy, indeterminacy, kinematic determinacy, indeterminacy. And then we were just starting with how to analyze kinematic indeterminate structures using force methods and displacement methods, and we were specifically focusing at the last part mainly on kinematic I mean displacement methods, because we saw they are advantageous in having a systematic way of solving these systems, right? So this is what we were discussing. Now in this session mostly I thought we will have an interactive session, a more conceptual discussion on the same, and see some important or intriguing problems, so that I thought it will be interesting to keep the session that way. We'll also solve the assignment problems, as I had got feedback from one of you that we can discuss the assignment problems as well. So before I get started, I want to know if you have any doubts or questions from the previous session, or from how the course is going on. Yeah, if your mic is not working, you can put it in the chat so that we can see. Any questions? Okay, then probably I can start with the question if you don't have any. So let me start with the question. This is a conceptual question on your basic structure analysis. So just try it out and see if you can solve it. Excuse me. So let's say that you have a simply supported beam with this is a pin and this is a roller, okay? And let's say there is moment applied on to one of its end. Then we have discussed in the previous class how to solve for the rotations and displacements at the ends, right? Now let's say that there is a not a n moment, but there is a distributed moment, okay? So something like this. So it is similar to a distributed load. Uniformly distributed moment is what I have in the structure. Can you find out what is the displacement and rotation along the span of the beam? Bending moment profile, shear force profile, deflection profile of the beam. Excuse me. Yes, Balachandra, you were saying something? Excuse me. So, can you find out what is the bending moment profile along the span? Right. How do we get started with? We solve for equilibrium equations and we find the support reactions, right? So let's say that we have this uniformly distributed moment to be m. Then what will be the reactions at the ends? So let's say the reaction here is this is B and this is A. So this will be RB and this will be RA, right? So if we take moment about this point, then what do we have? We have RB into, let's say the span is L, right? So we have RB into L is equal to M times L. Yes. So what is RB? RB is yes, RB is equal to M. So what is RA then? RB plus RA should be equal to 0, no? So RA should be minus M, right? So the reaction here will be like this and the reaction here will be like this. Both are equal to M itself. Fine. So what will be the shear force then? Shear force diagram. It should be easy from this point, right? Shear force should be equal to it's m. Yes, it's a rectangle where I'll draw it here. Let's say this is the beam span. Okay, so this is the shear force diagram that I'm going to draw. So it'll be rectangle, right? Because we have m and then it keeps constant and then it drops to 0 again, right? So this is shear force diagram. Okay, what is bending moment diagram? Bending moment diagram at any point, let's say I'm taking here, then what will happen? It's this reaction m into small x minus this is also m, right? M into small x. So it will be 0, which means that independent of which point I take, bending moment is going to be 0 BMD. Did you expect it? Okay. What will be the deflected shape for this beam? What do you think will be the deflected shape along the span? Deflected shape will be from bending moment. What do we get? Double integration of bending moment is what is deflection, right? Yes, if bending moment is 0, then deflection is also 0, right? So there's no deflection in the beam. So there are two questions here. What is happening to the beam? If I apply a load onto a beam, I expect some deflection, right? I expect something to happen to the beam. Only if the beam was entirely rigid, then I can expect that there is no deflection for a given load. So what is happening is the first question. Second question is shear force. We know that differentiation of bending moment is what is shear force, right? There might be a negative sign depending upon the sign convention, but let's say that magnitude wise the differentiation of bending moment is what is shear force, right? Then if I have bending moment itself to be 0, its differentiation is definitely 0 along the span. dm by dx is 0, right? Then how come shear force is finite constant here? Shear force should be 0, no? According to this formulation, is it not? Something seems to be very fishy here, right? Something seems to be off. So what is it? Any ideas? The understanding here is that for this, we how did we know this relation in the first place? How did we come up with this relation? dm by dx is equal to shear force V. We came up by first taking a beam and then take a small portion of a beam dx, right? So from a beam, if you remember the derivation, we took a small portion, okay, and then this dx portion we are just subject. We say that this is subjected to a variation of load, right? Q of x. This Q of x is varying, right? This is what would be the assumption if you remember. And then there is some bending moment at this point, and then there is another bending moment at this point. This is m of x, and this is m of d. It will be slightly different. M of x plus dm of x, right? So something like that we would have done, if you remember. So this derivation was based on the assumption that every small portion of the beam is subjected to only forces, not external moments. That's an inherent assumption while deriving this equation. We didn't, along with this q of x, actually we should have had plus m of x, a distributed moment. If we would have derived it this way, then we wouldn't have got this formulation. Therefore, this means that this derivation is valid only at places where there are no moments. Therefore, since this whole beam is subjected to uniformly distributed moments, this equation is not valid for this beam. Okay, that is the whole point. This thing is valid only at points where there are no external moments applied onto it. So therefore, we cannot say differentiation of moment is equal to shear force for this beam because it has entirely distributed moments onto it. So that answers the second question. What happens to the first question? First question is, what is the reflected shape? Why is the reflected shape 0? That means that is the bar not going to be affected at all due to the applied loads? The answer is yes, y of x will not change because the moment is 0. The bending moment is 0, therefore there will not be any curvature at any point. But then what change we can see actually in the beam is, let's say this is the beam that we are talking about. Then since there is a uniform shear force, what will be the deflected shape? You remember what will be the deflected shape of a shear subjected cube? In strength of materials you would have seen this, right? If you apply it to shear, then it will have shear deformations, right? The cross sections become tilted to the axis. Same thing will happen. This will just become like this. That's all. That is the only difference that you can see in the beam. So it's not like rigid. Since you're applying only shear forces, effectively this, even though we are applying a uniformly distributed moment, it's internally it's subjected to only shear forces. So therefore it will have only shear strains, no curvatures. Is this convincing? Any questions? Okay, so we can move on to the maybe we can discuss one more problem like this. Let's say that we have a load here and the load here. Okay, probably we can skip this problem for now and then go to assignments finish, because last time also we had to skip the assignments and then we were falling short of time. We'll go to assignments and quickly see those questions and then come back to this and discuss about it if time permits, right? Yeah, so this is previous year previous year assignment questions. We'll be discussing all three assignments because we couldn't discuss it last time. So let me know if something is very easy or something is very trivial, then we can skip that question and then we can go on to challenging questions, right? So what we see here is that we need to find out the static and kinematic indeterminacy of this problem. I hope it is very easy. So what you have to do is that static determinacy, we have discussed this in the session as well. So we have to find the total number of unknown reactions, right? So for the fixed support we'll have 3, and for the roller we'll have 1. But equilibrium equations are just 3. The full static indeterminacy is 1. What about kinematic indeterminacy? Kinematic indeterminacy, we can have only rotation at this end, right? Because we are assuming that it has no actual deformation, so this cannot move. So it's 1 and 1. So the answer is A for this. So I'll skip problems like this which seem to be very trivial from now on and then go only to a bit complicated problems. So the second question is, we have a fixed support and then we have like internal hinge as well, and then we have props also. So for this structure, what do you think is the static indeterminacy? Can someone find it around, say? What is it? Yes. 3 plus 2, 5. Yes. Yes. 0. Good. So the answer is uh, no. Something we are missing here. So no, yeah, actual deformations are not neglected here. That is one thing that is not stated here. So yes, so therefore we have to take 6 because the spinness has two things, right? So that's why the answer is B, 1. So you have to be careful. You have to see whether it's explicitly given actual deformations are neglected or not, right? Okay. So for the following frame, the number of static and kinematic indeterminacies are, we can ignore actual deformations here. So how do we do this? We have done a similar problem, right? So what do? We have a frame like this, and it's fixed, I suppose. So we'll just make it into two screens so that both are visible. Just a minute. Yes. Yeah. So let's say this is a structure we have. What is the static indeterminacy? How do we do this? We have to cut a section, right? So and then we say that we have these two structures, right? And how many unknowns are there? There will be three here. There will be three here, and these three are known because of Newton's third law. These will be equal and opposite. So we have three more unknowns at the space and this space. So there are totally 3 4s are 12. 12 unknowns are there. Yes. And how many equilibrium equations do we have? Only 6, right? 3 for this and 3 for this. So we have 6. So therefore static indeterminacy. But by the way, we can ignore axial deformations here. So we should not take it as 3 here, right? So there will be only two unknowns here. Two unknowns here. Am I right? So 2 plus 2 4 and 6 plus 4 is 10. So minus 2 we can do. Let's see whether we are right or not. So 10 minus 6 is 4. 4. So from this itself we can say, but kinematic indeterminacy, how do we find out? There can be, at every joint we can have a rotation, right? So we can have a rotation here, here and here as well. What other deformations are possible? That is it, right? No, there can also be displacement. It's a sway is also possible here, right? So there are two sways that are possible here. One is a sway at this level and sway at this level. What I mean by sway is that this displacement, total displacement, right? So you can have a displacement like this, you can have a displacement like this, and rotation as well. So it takes us to 5. So the option is, I think we made a mistake in static indeterminacy. It is 6. So how do we get 6 here? 3 plus 3 is okay. So the easier way to do is that just count the actual displacement also. So don't confuse it with here. So just ignore the statement actual deformations here and just take it as 3 and 3. Okay. So if you take it as 3 and 3, so you're getting 12. Yes, 12 minus 6 is 6. But then yeah, that is not seeming to be right. Actual deformation. Okay, actual deformations are ignored or only counted in kinematic indeterminacy. I think it should also be counted in static indeterminacy. That's just some mistake is what I feel. So how do we ignore axial deformation is that in total we know that yeah, so we should have included, instead of taking shear force and bending moment and axial force, we should ignore one of it. I think the answer should have been 4. Option A seems to be right to me. Okay, I'll anyway think about this and get back to it later in the next session. So find out whether the given truss is stable or not. How do we know? It's both are roller, right? Yes, both are roller condition, so it's unstable. Right answer is B. Yes. Find all the zero members in this truss. How do we find out? BD. BD, why should it be 0 BD? BE. No, no need, right? Yes, if we have a reaction and also we have, but at point C we can, yes, exactly. Point A, Yes, there is no load. Therefore, since they are inclined at an angle, both the forces should be zero. And same logic applies to point C as well. Yes, therefore these four members will become zero. Okay. So BC, CD, AB, and AE are the answer. Find the member force of CD for the following symmetric truss. So this I think you can do. It's a numerical problem. You just need to take a section at any point, and then either sections you can do, or you can do joint wise. So for this problem, maybe joint wise is better, is what I feel. So you can take this joint and then solve for these two forces, and consecutively you can proceed further to other joints and then find the other forces as well. Okay, so this can be solved. I hope this is easy to solve, so I'm skipping this problem. Yes, so next question is, if K is the stiffness matrix and S is the flexibility matrix and I is the identity matrix, then which of these statements is right? Yeah, but you're only checking about C, right? What about A and B? K is, so if we just rearrange this equation, we will get K is equal to S inverse, right? And we can also say that, yes, D is the option that should be right. Yes. Then there is a cantilever beam is subject to an anti-clockwise moment at the midspan. If the slope at B is theta, then what will be the slope at C? This is a very interesting question, right? What will be the slope at C? Since there is no load, what do we expect? Whatever deformation happens at this point, what is the answer? Same, yes. So it's understandable, because whatever deformation happens, since the bending moment is going to be only there within this span and not the span, the deformation will happen only at that span, and other things the displacement only will happen, there will be no deformation. So it will be like a rigid body rotation. Okay, so the rotation will be same. It will not curve. Okay, because bending moment is zero at those points. Okay, then we have another problem. Excuse me. So let's say we have a cantilever beam subjected to UDL with intensity W at its left half, so which is what is shown as case 1 here, and then tip deflection is 10 unit. Tip deflection means deflection at C, right? And the beam is subjected with the same intensity for the rest of the span, case 2. So in case 2, we have the whole beam subjected to the same load of W, 10 unit, right? So, and the tip deflection is 20 unit. The question is, what will be the tip deflection if the beam is subjected to WUDL over the whole span? Okay, this is also case 2, this is case 3. I'm sorry. So I read the question wrong. The question is, we are applying case 1 only the first half of the beam, yes, and the tip deflection is 10 unit. And we are applying only on the second half, not the whole beam. And then the tip deflection is 20 unit. Now if you are applying whole thing, what will be the tip deflection is what is asked. This is a, yes. So what principle are we using? Principle of superposition, right? So that is valid only if we have a linear elastic system, linear system. Need not be elastic, but yeah, linear system. Then superposition is valid, right? Okay. So answer is C, 30 unit. Okay. Now the next question is, a cantilever beam is subjected to 5 Newton at the tip C, and due to this load, its tip deflects by 1 mm. What will be the stiffness KCC? This is something that we had discussed last class also, no? So there is a force and there is a deflection. Stiffness is nothing but division of them, right? So force divided by deflection would give us a stiffness information. Answer is B, 5 Newton per mm, right? Okay, so this was a easy paper. Then we'll go on to the second week session. Yeah. So I hope you can see it, right? Yeah. So the question is, first question is, slope deflection method falls in which category of structure analysis? Which category? Displacement, because we take kinematic variables as the unknowns, right, and then solve for the rotations theta. So that falls in the displacement method of category. Second one is determine the degree of static and kinematic indeterminacy of the structure shown here. We have discussed this also in the previous lecture. So if it was just a cantilever, we'll have three. Other fixed unknown will just give three more unknowns. Therefore, three will be the static indeterminacy. But kinematic indeterminacy is zero. We know. Yes. So the option is D. How many degrees of freedom should be removed from this beam to solve it as a displacement problem? So displacement method. What is the answer? Think about it. The question is, how many degrees of freedom, yes, should be removed from the given beam. So the question is put in a different way, but maybe if I rephrase the question, you will be able to answer it. What is the kinematic indeterminacy of this structure? Yes, what does kinematic indeterminacy means? Kinematic indeterminacy basically means that how many extra degrees of freedom do we have, so that we are not able to solve it using displacement method. Not able, yeah. So here it is just a kinematically determinate beam. Therefore, we have zero excess. So that's what is a question put in a different way. Okay. So the next question is, I think it's a problem, but let's just read through the question first. So given there is a propped cantilever and there is a given load, determine the support reaction at B. So we need to find out support reaction. We have done a similar problem in the interactive session, right? So how do we solve it? We can, one of the best ways is to use method of consistent deformation, right? Yes. So and then we can find out what is the support reaction. What is it? Oh, good that you. uh, How much is it? 5 by 16, huh? 0.312. Oh, it's 3.125. Let's check. Yes, you're right. 3.125. Good. So, okay, we'll move on to the next question. What will be the size of the stiffness matrix for the given beam with degrees of freedom? We have different supports, and then what is the size of the stiffness matrix? So I think we haven't not discussed much on detail on this. Probably I can discuss that concept and then we can discuss this problem here, right? So last class what we were discussing was on how do we find out the stiffness for a single degree of freedom, kinematically single degree of freedom element, right? So we had an example of let's say we have an example of propped cantilever maybe, and then we said okay, so this has 1 degree of freedom. So if I give a moment at this point, what will be the rotation at this point, right? So that is what we were discussing last class, and we were saying that we can find out using the force methods, and we find that theta is equal to uh, 4EA by L, right? So ml by 4EA. If m is the moment that is being applied here, or in other words, m is equal to 4EA by L times theta. So this is what we were discussing last class. So this 4EA by L is what we call as a stiffness, right? And this was clear to us when there is 1 degree of freedom. Only one unknown is there, then we can derive it using force methods. Now let's say that we have 2 degrees of freedom. What do I mean by that? Let's say we have a system like this. Okay, then how many kinematic degrees of freedom are there? Kinematic indeterminacy is, can you find out the kinematic indeterminacy of this beam? 2. Yes. So basically we can have a rotation at this point and rotation at this point as well, right? So can we relate, let's say we are applying two moments at this point, let's say m naught and m naught, both are same also, let's say. Then can you find out what are the angles at these positions? So what I mean by angles is that there will be a rotation, right? So this will rotate something like this. So maybe I'll use a different color for the displacement. So let's say this will rotate by this, and because of continuity it will be like this. Yes. So something like this can happen, right? So if it is equal, then probably it will be something like this, symmetrical. Right, this is the probable deflected shape for it. Then so there are two angles here. One is angle theta here, which is same as angle theta here, theta 1. Both are equal. And then we have angle theta 2 here, right? So how is, let's say these two are moment m1 and m2, okay? Both are different. So how do we relate m1, m2 to theta 1 and theta 2? So this question is very similar to the earlier question where we had asked how do we relate m and theta. Yes. So here m and theta could be related using just a scalar value, and we have found out that. Here, do you think that we will have a number? So do we uh, do we expect that m1 will be something into theta 1 and m2 will be something else into theta 2? Do we expect this? Yes. I doubt it, because what this would mean is that if this was true, then what this would mean is that if I give only moment m1, there will be only theta 1, theta 2 will be 0. And if I have only moment m2, then theta 2 will be there and theta 1 will be 0 if m1 was 0. That is not actually true, right? Let's say that we have the same system. Just imagine that there was no moment here and we are applying only moment. Do we expect that it will behave like a fixed beam where there will be no rotation here and there will be only rotations at these points? So what I mean by that is, do we expect the rotations to be something like this? The rotation here to be 0. Is this what we would expect if m1 was the only moment that was there? No, right? We would expect that there will be some rotation here also. So something like this is what we would expect, right? So that means these two are coupled. What I mean by that is m1 will be something into, maybe I'll change the color. Okay, so what I mean by that is if m1 is equal to something into theta 1, yes, so why I'm doing plus is that I know that it's a linear relation because it's all a linear elastic property. So I know I cannot multiply or divide or something like that. It will become non-linear. Theta 1 into theta 2 means that it's a non-linear equation. Okay, so basically I know it will be a linear relation. That's why I'm doing this. And same logic I can do for m2 as well. I can say that it's something into theta 1 plus something into theta 2. This something is what we are going to call as stiffness. We know it's similar to stiffness, right? Last time also we had only one variable. Now we are having just uh, four quantities instead of only one quantity. So those quantities I don't know what they are. So let's just name it as k11, k12, and k21 and k22. I don't know what they are, but I know that there will be four numbers here, right? So now I can just write it in a very efficient format instead of writing like this. I know that a system of linear equations can be written in a matrix format, right? That's what I have learned from my engineering mathematics. So I can write m1 m2 is equal to theta 1 theta 2 k11 k12 k21 and k22, right? Now how do I find these numbers? How do I find these numbers? So how did I find the stiffness for the first case? I'm going to use the same logic here. So for the first case, what did we do? We have only 1 degree of freedom. We solved it using structure analysis, right? So what did we do? For a given moment, we found out what was the angle, right? Now, so basically I know that I have to use structure analysis to solve this. So to solve this, what I will do is that since these are two variables and it becomes difficult to solve both of them, so what I will do is that I will just assume that let's say theta 1 equal to 0. This is always true for all theta and all m. right? So this is a general equation. So what I can do is that I can just substitute, let's say theta 1 equal to 1 and theta 2 equal to 0. I can do anything, and I'm just substituting these two random numbers to the matrix. So what will happen if I do this? I'll know that what m1 is equal to whatever m1, let's say m1 dash, because I'm substituting the values. It's m1 dash is equal to k11 into k21 into this will become 0. So on m2 dash will become k21, right? What I mean by that is I'll multiply this and this and this has become 0, therefore I get only k11, and for m2 dash I get only k21 because k22 into theta 2 will become 0. I mean, what this actually means is that k11 is nothing but the moment that is produced or needed to make theta 1 equal to 1 and theta 2 equal to 0. Is it not? That's what it means. So k11 is that moment m dash such that theta 1 equal to 1 and theta 2 equal to 0. When will that happen? It will happen when I enforce theta 2 equal to 0. That means that I have this structure. I have this structure, right? This is what my structure is. So what will be this? What will be the moment needed so that I have theta 1 equal to 1? I already know this thing. If there was only one fixed, this is a propped cantilever, right? Two propped cantilevers in parallel. We have seen this last class as well. So if I give a moment here for one propped cantilever, it's 4 by L, and if there are two propped cantilevers and if both are identical, then it is 8 by L, right? So I know stiffness gets added. So therefore I know that this will be just 8 by L. And what does this mean? This is the moment m2 dash such that theta 1 equal to 1, theta 2 equal to 0. So when will that happen? What will be the moment that should be given here so that this is 1 and this is 0? So basically what are we doing? This is a fixed end moment, right? So that is nothing but 2 by L, right? So I think I made a mistake here. Yeah, it's correct only. It's correct only. So it's 2 by L. Now 4 by L is to give the moment. If you remember, 4 by L is a moment that we are giving here so that theta 1 equal to 1, and then half of it will be produced here, right? So that is the moment that is being produced or need to be applied. There is actually no fixity here. I am just drawing it here to mean that theta 2 should be 0. But there is no fixed beam. Actually it's a pin beam, pin end, right? So I have to provide a moment of 2 by L at this point so that I know that I know that the theta 2 will be 0 and theta 1 will be 1, right? And same concept I can, as with similar concept I can find out what is k12 and k22 as well. How do I do that? For that I need to just make theta 2 equal to 1 and theta 1 equal to 0. Basically what I'm doing by substituting these things are decoupling. If I put one thing as 0, then it will become decoupled, right? So by decoupling it I'm finding these values. Once I find those values, I now know what is the relation between m1 and m2. Just like how I know how I had only one stiffness value, now I'll be having a matrix. This matrix will become known to us, right? So with this is what we would be doing in subsequently in this course. So this is what is the gist of what we would be doing in a matrix method of structure analysis. We'll be using matrix to solve structure analysis using displacement based methods, right? Kinematic variables is what we keep as unknowns and then we'll solve for them. Now I think we can talk about, we can go back to the question that we were discussing. So the question is, what will be the size of the stiffness matrix? So the stiffness matrix that we are talking about here, right? So what you notice is that here is that whatever is the kinematic indeterminacy of the structure, that much will be the size of the stiffness matrix, right? Because then only it can multiply with that many kinematic indeterminacy or degrees of freedom, right? So the multiplication is possible only when the degrees of freedom and the size of the matrix is the same, right? So that's a concept. Yes, so basically we know that there are 6 degrees of freedom. They themselves have marked it here, right? So for all the 6 degrees of freedom, we'll have a 6 by 6 matrix. Okay. What is the next question? Find whether the truss is stable or not. What is it? Is a truss stable? Basically, we can use Maxwell's rule to find it out, or even by visualization, we can see that this is a not triangle, right? Yes, so it's not a triangle. Therefore, we might probably need one more member here, right? So just by visual inspection, we expect it to be unstable. But if you want a convincing answer, maybe Maxwell's rule will be able to give a better indication for that. Okay. Next question is, which figure shall we use to determine the elements of the second column? Okay, corresponds to degree of freedom number 2 as shown in the structure of the flexibility matrix. So the question here is, so flexibility matrix was, what flexibility matrix means is that instead of writing it this way, M is equal to, let's say this matrix is just denoted as S, okay? By this M I mean the whole M1 and M2, and this by S I mean the whole stiffness matrix, and by theta I mean the whole theta 1 and theta 2, right? So this is what I mean in a vector equation, yeah, matrix equation. So I can just invert this and say theta is equal to S inverse M, right? I can take S inverse on both sides and I'll get this. So this S inverse I can just call it as some F, right? And that F is what is called as a flexibility matrix. Okay, so it's nothing but inverse of S. So the question here is, which figure shall we use? So basically, how do we find out this? Right now we saw how to find out the columns of a stiffness matrix, right? How did we find it out? Whichever column we need to find out, if you notice that corresponding degree of freedom we need to assign 1 and other things we have to assign 0. Is it not? So same thing we are going to do here. So basically if we have to do for 2, then for second column, second degree of freedom we need to assign a value of 1 and other degrees of freedom we need to assign it as 0. So basically we need to have a so this is a translation degrees of freedom. So translation degree of freedom we need to just assign 1 unit displacement and then everything else to be 0. So we would probably expect a C is a expected shape that we would keep to find out the flexibility matrix. Okay, I'm surprised. Actually, I would also keep the degrees of freedom corresponding to 6 and 3 to be 0, right? If I make them to be 0, then it should be 0 slope at these 2 points. That's what I would expect. Maybe there is a, uh, it should have been 0. That's what I'm expecting. Because otherwise B and C are looking very same. I would expect that the slope here should be 0. Because then only these degrees of freedom will also be 0. Okay. Anyway, I'll get back to it if there is a change in what I think. Fine. The next question is, suppose a structure has static indeterminacy of 4 and kinematic indeterminacy of 5. How many redundancies should be considered to solve it using force method of structure analysis? This question is very interesting. 5. The question is force method, not displacement method. So force method means we should, yes, we need to think only about static indeterminacy. So it's 4, right? So the answer is B. Next question is, in the given structure stiffness matrix, which columns corresponds to degree of freedom 2? Just now we had discussed about it. If we are talking about degree of freedom 2, then we are talking about column 2, right? So it's second column. Okay. What will be the equivalent joint load for the point B of the given beam? So this also we have not discussed. Then probably I can just discuss that concept before we see this. Okay. Okay. This okay. That I'm not sure. If there is a change in the numbers, then probably it will be intimated. But then, okay, what did you do? Can you summarize what you had done in the thing? So basically, how do we find out equivalent joint load at point B? We just need to find out the fixed end moments, right? Yes, fixed end moment. Possibly you can use conjugate beam method also. Yeah, you can use that method as well. So here, okay, okay. I'll just check the values once and then sum submit it. Okay, that's fine. I'll check the values and then I'll let you know if there is a change or if there is something. Okay, so the method to adopt is that we need to use find out fixed end moments. That's what they're asking, right? So the concept is what? Yes, the fixed end moments and the reactions. Yes, for the given loading conditions. Okay, shall we move on to third week? Okay. So this is about matrices. So this is based on matrix basics of matrix analysis, right? So suppose A is an orthogonal matrix and B is an inverse of A. So what would be the value of A transpose? So do you know what an orthogonal matrix is? So this we would have come across. The definition of orthogonal matrix is that. So at this point, I assume that we know what transpose and inverse are of a matrix. So transpose of a matrix is just means that we are interchanging the rows and columns of a matrix. So basically, a matrix is a matrix B is said to be transpose of A when the rows and columns of A are interchanged and it becomes a new matrix B. Okay, so that's what is the definition of transpose. And inverse basically means that what is a matrix. Let's say there is a matrix B that when multiplied with another matrix A gives identity matrix, then we say that, and also the other way it's true. So AB is also equal to identity matrix. Then we say that A and B are inverse of each other, right? So we have a symbol as A inverse. Okay, these are the basics that we have to know. And by orthogonal, what we mean is that a matrix A is said to be orthogonal if its inverse, which should be a new matrix, happens to be same as its transpose itself. Okay, so this does not happen for all matrices, but if this happens, then we call this matrix A to be orthogonal, right? So by that definition, what do we see? A is an orthogonal matrix and B is inverse of A. What will be the value of A transpose? Is the question. Is equal to B, right? So the option is C because A transpose is A inverse and we know A inverse is B. Okay. Next question is, if A is a m by m matrix and B is also a m by m matrix obtained by multiplying each element of A by a scalar constant P, okay, then which of the following statements is true? Yes, yes. How do we know that? Because we can take out P from, yes, we can take out P from every row and then it will happen to be, we'll be multiplying it m times when we take out, so it will become P per m. Okay, we can take it from each row, not every element. Okay, so that's how we that's a property of a determinant, right? Fine. So suppose that we have a following matrix. Suppose the following matrix is A is decomposed into a symmetric and a skew symmetric part U. I hope you are aware with what is a skew matrix and a skew symmetric matrix. What is a symmetric and what is a skew symmetric matrix, right? So let's say we have a matrix A. What is the symmetric part of it? So what is a what is a symmetric matrix? Yes, a matrix is said to be symmetric if its transpose and the matrix itself are the same. So an example would be something like 1, 2, 2, 3. right? What it means is that the off diagonal terms should be, so what this is A, if I transpose it, what will happen? This row will become column and this row will become again the next column, and then we see that both are actually same. That's what happens, right? So this is a symmetric matrix. So and a skew symmetric matrix basically means that, yes, if it happens to be this, so what this means is that, let's say I take some matrix, let's say 3 by 3 matrix. Okay, 3 by 3 is difficult for me to write. I'll just give an example of 2 by 2, right? So basically, if I transpose this, then I'll get 0, 2 and minus 2, 0, right? So observe that it's just negative of each other. This will happen only if the diagonal terms are essentially 0 and off diagonal terms are negative to each other. Okay, so that is a condition for skew symmetric matrix. So that being the case, now the question is, a matrix is decomposed into symmetric and skew symmetric. What it means is that although not all matrices are either symmetric or skew symmetric, it can be shown that every matrix can be written as a sum of a symmetric and a skew symmetric matrix. And how do we do that? We can just write the symmetric part to be A plus A transpose by 2, and we can just write the skew symmetric part to be A minus A. Right, we can see that this is a symmetric part because if we take the whole transpose, this will again be the same thing. But if we take the transpose of this, it will become negative of its. And we can see that when we add both of this, we will get A. So that's how we show it. Okay. Now the question is, what will be the product of S and U? So how do we do that? Yes, we just find out S and U and then just multiply them. That's one of the easiest ways to do it, right? And how do we find out S? We know this thing. You find out U and then multiply both of them. So we can do this. It's a calculation problem. Link to question 1. What will be the determinant of matrix A? So we go back to question 1 and then we say that orthogonal matrix, and what is the value of determinant of A? Oh, sorry, I think I skipped a question. Yeah, sorry. Link to question 1. What will be the determinant of matrix A? Oh, I think, yeah, so this is just a previous question. Okay. Yeah. Linked question means just linked to the previous question. Okay. And we can just find the determinant of it. Determinant, I think it's known to all of us. So we just find out the determinant of this matrix. In MATLAB also you can just find it using det. Okay. So determinant should be findable. Yes. So then the question next is, what will be adjoint of matrix A? Adjoint is the matrix of transpose of cofactor matrix, right? So what a cofactor matrix is? What is a cofactor matrix? Yes, yes. So basically we take minor of every element and then we substitute with appropriate signs. Yes, plus minus gets alternated. And if we do that, we'll find out the cofactor matrix, and then if we take the transpose of it, we get the adjoint matrix. This is also a calculation intensive problem. We can do it. What will be inverse of matrix A? So yes, we can either do it. There are multiple methods to find out A inverse. One of the easiest method is that A inverse is equal to, yeah, Gauss Jordan also you can do, but you can also use formula because in the previous step we have already found out adjoint of A. So inverse of A is nothing but adjoint of A divided by determinant of A. That's why they have asked us to find out first determinant, then adjoint, then asking the inverse. So divide both of this, you will get the answer for inverse. Okay. And Gauss elimination is generally used to solve system of linear equations. After Gauss elimination, the square matrix becomes upper triangle. Perform the Gauss elimination to matrix A to find the upper triangle. So you can do this. So basically, how do you do Gauss elimination is that you do a series of operations onto it, and then you convert it into an upper triangular matrix, right? So you can subtract two rows. So there are three rules you can adopt to solve this linear do operations on a matrix. What are the three rules? Do you remember? First is that you can multiply any row, let's say any row or column, but just stick to rows. So it's also equally applicable to a column. Any row can become k times of, so I'll just write I, right? Any row can just become k times of itself, where k is a real number but not equal to 0. Yeah, it's a scalar but not equal to 0. Okay, and then what is the second rule that we can do? Yes, interchange should have been the first rule. Yes, you are right. So we can interchange any two rows. Okay, and what is the third rule? Yes, so a very generic way of saying that is any row is itself plus k times of any other row. Yeah, k can be negative, right? So therefore negative is also included in it. K can be anything except 0. Okay, but here it can also be 0. It wouldn't matter because rj will remain rj only. Here only it should not be 0. Fine. So those are the three rules that we can use to perform different operations such that we can make these three, the lower triangle to be 0. Once we make that, then we can solve the system of linear equations. With the help of upper triangular matrix, you is actually find the solution. So once you do this, then you should be able to solve the system. So that is self-understandable, I guess. Find the solution of the following system of equation using concept of block matrix. This is also again you can solve using the concept of block matrix. It's covered in the course. You can just go through it, right? So there are only two variables, and here there are two variables. You can equate it to find out all the four variables here. Find the rank of the following. You can again find rank. What is a rank? Rank of a matrix. What does it broadly mean? So, e- e- Yes, echelon reduced matrix, we have to find out what are the number of non-zero rows. But other more generic yes, if determinant is not equal to 0, that means yes, we know that rank will be equal to the yes, we know that. But if it becomes 0, we don't have any clue. We just know that it is lesser than the size of the matrix, but we wouldn't know how much lesser, right? So what it basically means is that how many number of independent rows or columns do we have in the matrix is what is the indication of rank, right? So if rank is not full, let's say rank is only 2, that means that there are only uh, two independent rows or columns we have in the matrix. That's what it indicates to us, right? So you can just use the previous these operations and then find out the row echelon reduced format, right? And then see how many uh, zero rows or columns are there. Then you can find out zero rows are there. Then you can say how many ever is left over is the rank, right? So I think all these are pretty straightforward from the course that has been covered, right? Okay. So probably we can stop it here and then discuss with other questions in the next session. Yeah, thank you.